Today we're going to be talking about radiation. This is the last part of the class. So we went through conduction first, and then we used our concepts from conduction to talk about convection. Convection is just conduction with moving fluid. Radiation is something really different entirely. It's unlike conduction and convection, where the energy carriers are moving heat by collision between molecules or mass flux in a system. Here we have energy that's being transferred from one body to another body across a void in space, or across some region that's not actually participating in the heat transfer. So the phenomenon is a little different, but the way we treat it in terms of rate equations ends up looking pretty similar. So what is radiation? Let's kind of think about what's happening in some bodies. Let me draw first. This is our material, and inside this material, so we've got this is the surface up here. So radiation is happening every time you have some molecule. It has some electron state associated with it. There's a change in the electron state, a drop from one shell to the other. You get this emitted photon, or some emission of energy. And that can happen whether, say, you're inside the material here. You could have an emission of energy from a little energy carrier. But if you're inside the material, it's very likely that that is going to be immediately absorbed by whatever's around it. Right? So it's emitted, and it's pretty much immediately absorbed. If you're, however, on the surface, right, the molecule's on the surface and it emits, there's a chance that that molecule or that photon could be emitted out into space, right? And there's nothing there to necessarily absorb it right away. So we tend to think of radiation as what we call a surface phenomenon. Right, so radiation is a surface phenomenon. It's not that radiation is only happening at the surface, right? It's happening everywhere. It's just that it only manifests at the surface because that's where there's a lack of anything to stop the radiation when it does occur. Okay, so we call it a surface phenomenon for that reason. So a couple just maybe definitions that we're going to need or use as we go through this. We're going to talk about radiation in terms of its wavelength or its frequency. So if we have some we'll just kind of draw the path of a photon here. Right? So it's got this kind of wave property associated with it. The distance between the peaks here, right? We usually call this lambda, right? So we're calling this lambda. This is going to be our wavelength. And we usually define this in terms of microns, micrometers, right? So the peak-to-peak difference is going to be our wavelength, and then the photons usually traveling at the speed of light, which we refer to as c. That's, for an engineer's purpose, usually around 300,000 kilometers per second. Okay, and there's a couple of relationships here between speed of light and wavelength. So we say speed of light c is equal to wavelength times the frequency. So there's a couple of ways to write frequency. I usually write omega. I think the book uses nu. Nu is used like 5 different ways, so we'll stick with omega for now. So then the energy that's associated with the photon is equal to h. Again, h is an overused constant. H in this case is the Planck's constant. Okay, and then times omega, which is also equal to just h over the wavelength. Okay, so if you're given wavelength, you're given frequency, you can always convert back and forth just based on the speed of light. All right, so that's just really generally what radiation is. Back to the idea of what is it that we see radiation, and how does it sort of apply to us as we're engineers in heat transfer. So here's a little chart from the book that shows some of the different ranges that show up with radiation. So there's a lot going on here, but there's kind of this spectrum, obviously, of radiation. We go from really short wavelength, like 10 to the -8th, up to really long wavelength, 10 to the 10th. So these huge orders of magnitude and difference in the energy that's carried and the wavelength that's associated with a particular form of radiation. But we go anywhere from, on the very short wavelengths, things like gamma rays, cosmic rays. These are super high energy rays that are extremely damaging if they hit humans, right? They really disrupt your molecular structure. To things like thermal radiation, right? This is this kind of region here. Thermal radiation, this is associated with the sun. The most, like something like 99.9% of the radiation emitted from the sun, and it comes in this thermal radiation window. And then out here in the longer wavelengths, we have things like radio signals, low energy stuff. So we're constantly being, say bombarded is a strong word, but we're constantly experiencing radiation from radio, other communication signals, but they're so low energy that they don't really interact with us. So yeah, we focus really on this thermal radiation window here. Within the thermal radiation window, we have the visible spectrum, right? So the visible spectrum is here, and that goes about 0.38 to 0.78 micron. So everything that we see, red all the way up, is going to be in that region, that visible region. So there's quite a bit of stuff coming from the sun that's outside that visible region, of course, but something like half of the radiation emitted from the sun is in the visible region. Let's see what else here. Okay, so that's I think a quick synopsis of radiation. Again, we spend most of our time worrying about thermal radiation. And why do we talk about thermal radiation and this not the other parts? Well, it's because one, radiation we experience is pretty abundant in that region. Also, it's high enough energy to have an impact thermally. Right? Ultimately, if you're a physicist, you might think more about cosmic rays or gamma rays, whatever. But we care about the thermal part because that's the part that's generating heat in our systems. And we need to think about how to deal with that. Right, so thermal radiation is going to encompass both the solar portion here, but also like us, right? So we sitting here emitting at 300 Kelvin exist kind of in this region. Okay. So one way that we normally think about, the first way we can think about radiation is radiation from a surface. And when we talk about radiation from a surface, there's an idealized model, which is something called a blackbody. And then there's real surfaces that don't emit quite like a blackbody. We're going to start talking first about blackbody emitters and how they behave and get a handle on those, and then we'll move to real surfaces later. So if you're a surface out in space, it's our little surface in space over here, you're going to be both emitting radiation. So you're emitting radiation here, emitting radiation. You're also going to be absorbing. Right? You're absorbing radiation. When we talk about a radiating surface, it's not usually enough just to talk about the emitting part. The emitting part is actually the easy part. If we know something about one surface, we know its temperature, we know its surface area, we know its orientation, we can say how much light or how much radiation that surface is emitting. What's a little harder is figuring out what's that surface absorbing, because that depends on everything around that surface. Like, this wall here, it's easy to say this rectangular wall is emitting something, but to see what it's absorbing, we have to figure out all the different sources, you guys included, all of us standing here, our temperatures, our orientations, all of that. So that absorbed part of it's actually a lot more complicated. Normally what we do is we just say, all right, if you're absorbing, we call this like T surroundings. So we give an effective average surroundings temperature, and we use that to describe the radiation that's coming back. That's obviously just an approximation. Okay, so we have these black bodies. We have to think about the emitted and the absorbed radiation. Let's actually define what a black body is, or give some properties of it. Okay, so a black body, a black body emits the maximum possible radiation. It's the maximum radiation possible for a given lambda, wavelength, and temperature. So for a surface that has a certain temperature, you pick a wavelength, there's a maximum theoretical emitted power associated with that temperature and that wavelength. Right? And for example, if we look down here at our little chart, we could say, all right, each of these different curves here are blackbody curves associated with a single temperature. So they're saying I have emitted power right over here on this axis here. I have an emitted power that's a function of my wavelength. So I could pick out and say, yeah, at this temperature, 5,800 degrees Kelvin, this is the maximum possible radiation that could be emitted at about 1 micron. Right, so no surface could possibly emit more than this blackbody surface could. It's an idealized surface in that way. Okay, so the second thing that's true of black bodies, why we call them black bodies, is that they absorb all the radiation that hits them. Radiation that hits the surface. And so they're perfect absorbers. And if you think back to maybe your undergrad heat transfer, if you had it, if you have a perfect absorber and a perfect emitter, they're actually the same thing, right? It's absorptivity of 1 is equal to an emissivity of 1 for a black surface. So it looks black to us because it's not reflecting any light, but it is also a perfect emitter. Okay, third thing here, it emits radiation uniformly. It emits radiation uniformly in all directions. Right, so we call this diffuse, the diffuse surface. And think kind of conceptually, what is a diffuse surface going to look like? So if a surface is emitting radiation and it's diffuse, then it's going to look to the eye kind of like this dull surface. Right? It may have a glow to it, but there's not going to be any way of looking at that surface and discerning anything about, like a reflection off of it or anything like this. It's kind of just a dull, glowing surface. And actually, most of the things we do see that are emitting surfaces do have this property of being diffuse. Practically, what it means is it's emitting a ray, it's emitting a photon in any direction randomly. There's no directionality associated with it.